Hello and welcome to our lesson on factoring as a review. We're going to be working our way towards solving new types of equations, trigonometric equations. But before we get there, we got to talk about some trig identities, which again, we'll get to this, but in the process of working with those identities, it's going to require factoring. Now, factoring is really a skill that is used in just about every math class you can think of, computational math class you can think of, and a lot of times we forget how to do it, so it'll be a good review for us here. But not just that, the way that we're going to be factoring with the trig expressions we're going to see is it's different. So we got a good foundation of review here. Hopefully that will carry over until we start to factor with trig identities and trig expressions, and then ultimately, again, this is going to allow us to solve new types of trig equations. So let's do it. What is factoring? When I say that, is anything popping into your head? I hope. Factoring is basically the process of taking one polynomial and rewriting it as a product of two or more polynomials. You can also think about it as the reverse of our multiplying process. So for instance, in this product, if I gave that to you, I'm hoping you would instinctively say, okay, this needs to be distributed, so we would multiply, and the 2x squared times the 3x squared would give us 6x to the fourth, where we're multiplying those coefficients and adding those exponents. And then we would multiply, and I don't know why my pen just did that. We would multiply here, 2x squared times 5x, and we would end up with a 10x to the third. And we would multiply here, 2x squared times the negative 4 would give us a negative 8x squared. So starting here and working this way, that's the multiplying process that we've seen a bunch of. What we're doing when we're factoring is the reverse. Instead of starting with a product, we start with this one polynomial, and we have to figure out what two polynomials did we multiply to make that thing happen. So when we start with the 1 and rewrite it as a product, again, that is what we're doing when we are factoring. Now, normally we're thinking about the opposite of multiplying as dividing. There will be definitely some dividing happening when we're factoring. And when we factor, each of our factors ends up being a factor of the polynomial we start with, so it will divide evenly into that polynomial. But again, factoring and multiplying we can think of as opposites in terms of our polynomials, and later our trig expressions. So when we're factoring, when we're working in reverse, before we actually start the process, we need to make sure that the terms in our expression are in descending order, or for a polynomial, we would just refer to that as standard form. So we want our highest exponents, our highest degree terms to be first, and then they would descend down. So if we start with an x cubed, x squared should be next, x to the first would be third, the constant should always be at the end. So if we were going to try to factor this expression, we would start by putting it in order. 3x cubed plus x squared plus 2x minus 4. Then we're going to go about our business factoring. So before we factor, let's make sure we're in order. Now, when we're ready to start factoring, the number of terms in the expression is going to dictate how we factor, but regardless of the number of terms in your expression, the first step in any factoring process is, if possible, to factor out a greatest common factor. And we saw this a little bit with our phase shifts. Remember, we had our let's say 2x minus pi in the standard form of one of our functions. We would have to factor out the 2 and make that x minus pi over 2 to actually see the phase shift. So that's the process of factoring out a GCF. It's the first step in any type of factoring process. So for example, with the 72x squared plus 2 here, I was trying to circle that, we're looking for something that goes into both of those terms. So in this case, they're both divisible by 2. We would factor out that 2, and that would leave us a 36x squared plus 1. Now in that case, GCF is all we can do, so we would actually be done with the factoring in this particular problem. If you look at the next example, there's still a GCF of 2, but when we factored out, we're left with this 36x squared minus 1. That's what we call a difference of squares. I'm hoping it looks familiar to you. So in this particular case, after the GCF, we would continue to factor. Oops, can't spell. Continue factoring, and we'll talk about how to continue, or review how to continue in just a moment. And then sometimes there isn't a GCF, so if we were already sitting at 36x squared minus 1, then we would go ahead and continue factoring. So GCF is a first step. We want to take it out if it's possible. Sometimes after we take it out, we're done. Sometimes after we take it out, we continue factoring. And sometimes we can't take it out and we're going to factor anyway. So all three of those situations we're going to see. Now it's the what do we do to continue factoring? Well, the process that's used to continue factoring is, again, based on the number of terms. If there are 4 terms, like the first example we looked at, actually the second example, like this guy, if there are 4 terms in our expression, we're going to use a factoring process that we refer to as grouping. If there are 3 terms in our expression, there are about, I don't know, I can think of a dozen different ways that are taught for factoring with 3 terms. Some people use guess and check. Some people use something called split the middle. I use a process referred to as bottoms up. So I'm going to show that to you here. If you like it, use it. If you are already comfortable factoring trinomials using a different method, you do not have to use my method, but I'm going to show it to you in case you don't have a method, okay? Or maybe you'll like mine better than what you've used before. So 4 terms are grouping. 3 terms, I'm going to show you a process called bottoms up. If there are 2 terms, like we see happening here, we're only going to be able to factor those 2 terms if there's a GCF, and we saw that in this one, or if those 2 terms represent a difference of squares, which is actually what 36x squared minus 1 is, or if it's a sum or difference of cubes. Okay, so make sure we're in order, take out the GCF if we can, and then, if there are 4 terms we group, 3 terms we'll use bottoms up, 2 terms we're looking for a difference of squares or a sum or difference of cubes. So what we're going to do today is review these processes, right? These processes applied to polynomials in this case with those number of terms. Now, eventually we're going to, like I said, take this to trig expressions. We're not looking at polynomials anymore, but the same processes will apply. Alright, so let's talk about grouping first, and again, I'm hoping this looks familiar to you. You've all been through college algebra, so we should be pretty comfortable factoring. When we're grouping, let me just show you how it looks, then I'll go back to the steps. We're looking for a greatest common factor, but the 4 terms in our expression don't have it. So what we want to do is sort of look at this thing in 2 different groups. So I like to put a line in here, not that that's a mathematically correct thing to do, but it's just helping me separate these 2 terms from these 2. Because if I look at those 2 terms or 2 sets of terms separately, each of them has a greatest common factor. So nothing goes into all 4 of these, but if I want to focus just on the first 2 terms, these 2 have something in common. They have in common an x squared, and so I factor that out, and when we're factoring this GCF out, we're dividing. That's where that opposite of multiplying comes from as well. So I'm going to be left with an x minus 3. If I look at these 2 terms, they have something in common as well. They have in common a positive 5, so I factor that out, and that's going to leave me an x minus 3. And so if you look at what we have at this step, we no longer have 4 terms in our expression. Now if I multiply out what I have, I do get back to the same 4 terms, so I haven't changed anything. But now again, instead of 4 terms with nothing in common, I have 2 terms. This product means this is all 1 term, and this product means this is all 1 term. And what do those 2 terms have in common? Well, they both have an x minus 3, which means now I can factor out a GCF from these 2 terms. It's just that my GCF is an x minus 3. So I factor out my GCF of x minus 3, and when I factor that out, remember I'm dividing, what's going to be left? Well, if I divide it out of this term, it's gone, it's divided out. What's left is x plus 2, or sorry, x plus 2, it's x squared. If I divide it out of this term, again, this is going to divide it out, what's left is the 5. So I'm going to factor out the GCF of x minus 3, and that leaves me an x squared plus 5. So this is getting factored out, and this is what's left over. And there we did it. We took our one polynomial and rewrote it as a product of 2. Again, if I was to multiply out these 2 binomials, I'm going to get back to these 4 terms that I started with. It's kind of a nice feature of factoring, as we could check our work by multiplying. Okay, so the idea with grouping is you're going to split the 4 terms into 2 groups. I do that with a vertical line, but you don't have to. What you're trying to do is factor out the GCF from each group, and that's going to leave you 2 terms, and those 2 terms are going to have a binomial GCF that you can then factor out to finish up the problem. So you're looking for a GCF, factor it out, and then you're taking out a GCF again. It's just a binomial GCF. You factor that out, and then you're done. So if this is something you've seen before and you feel comfortable, maybe pause the video and give this a try. Otherwise, we'll knock this one out together again. Terms are not in order, so I'm going to start by taking this thing and 3x squared should be second here. Then the minus 4x, the constant, should be at the end. And then I'm going to look at it in two groups. First group, I can take out a 3x squared, which is going to leave me, if I divide this out, a 2x plus 1. Second group has in common a 2, and when the first term's negative, we're going to make that GCF a negative 2, so that'll be a 2x plus 1 that comes out. And if you had forgotten that little rule, like let's say you took a positive 2 out here, this would be negative here and negative here, and then this would not match this. And if those don't match, not in common, can't continue to factor. So that would be your clue to, oh, let's make that a negative so that this all matches up. So again, this would be negative 4x and negative 2. So factor the negative out with the GCF when that first term's negative. So now instead of 4 terms with nothing in common, we've got 2 terms. They have in common a 2x plus 1. I'm going to factor that out. And that's going to leave me a 3x squared minus 2. And I'm done. Took my one polynomial and rewrote it as a product of 2. Okay, so that's a process of grouping, which is basically just factoring out GCFs. Hopefully one of the processes that you're comfortable with and have seen enough. Now, it's the factoring of trinomials that, again, there's probably about a dozen different ways I've seen this taught. I don't know where you're coming from. Maybe you're perfectly fine using guess and check or split the middle or some other process to factor this. If that's the case, totally acceptable, fine. Use whatever method you can to get that thing factored. What I'm going to use is what I've seen to be the most efficient way to factor a trinomial. So let me show it to you, and then I'll go back and put the steps in, okay? So what we're going to do when we're factoring with bottoms up is we start, let's go crazy with the zooming, no. We start by multiplying our first number and our last number. So when I multiply 2 times that negative is connected there, 2 times negative 6, I get negative 12. And what I'm going to try to do is find factors of negative 12 that add to my middle number, which is a negative 1. So when I say factors of negative 12, I mean like 1 times 12 is 12, or 2 times 6 is 12, or 3 times 4 is 12, right? Those are all the pairs of factors. Now, if this is negative, that means one of my factors would have to be negative to make the product negative. So if one of my factors has to be negative, then I'm looking for sum of those, like actually a difference to make the negative one that's here. So like the difference between these two is 11, that's no good. The difference between these is 4, that's no good. But the difference between this last, oh my gosh, that's my eraser. This last pair is 1, that's going to be the pair of factors I'm going to use. So I'm looking for two numbers that multiply to negative 12. So I said 3 and 4 are going to get me 12. And I need them to add a negative 1, so if I make the 4 negative, then now those two numbers multiply to negative 12, and they add to the negative 1 that's in the middle. And I'm making a mess here. So that's 1, and okay. So no, you multiply the first and last number, and you find factors of that product that add to the middle number. Once you have your factors, you're going to divide them by your first number. So I'm going to divide this by 2, and divide this by 2, and that creates two fractions. Those fractions we're going to reduce if we can. 3 over 2 doesn't reduce, so I'm not going to mess with that one. But negative 4 over 2 does. Technically that divides to make a negative 2, or as a reduced fraction I could call that negative 2 over 1. And the reason it might be helpful to see it as a fraction is because once we have the fractions reduced, this is where the name comes from, we read them from the bottom up to get the two binomials that we would multiply to make this trinomial happen. So when I'm reading this one, from the bottom up, I'm going to read this as a 2x and a positive 3. That means that 2x plus 3 is one of my factors. And this is a 1x and a minus 2. So 1x minus 2 is going to be my other factor. And multiplying out those two binomials would produce this trinomial. Okay? So that's what bottoms up looks like. Let me show you one more time and then we'll go to the steps. So this one, I don't know if you need a process for it, but again, multiply your first number, it's 1 and 72, makes 72. Find factors of positive 72 that add to negative 17, like a negative 9 and a negative 8. They multiply to positive 72, they add to negative 17. We divide them by our first number, and then reduce if we can. Well, these don't reduce, so 1x minus 8 is going to be a factor, and 1x minus 9 is going to be a factor. And I'm done. Alright, so bottoms up, it's wonderful, it's fast, it's efficient. You start by multiplying your first and last numbers, and then you find factors of that product that add to the middle number. Once you find your factors, you divide the factors by your first number. And obviously, creating two fractions, you want to reduce if it's possible to reduce. And then here's where the name comes from. Once you have those fractions reduced, you read the reduced fractions, it has to be reduced, from the bottom up. Okay, so, and that's going to give you the binomial factors for your trinomial. So for example, if you reduced a fraction, you ended up with 1/3. Again, reading from the bottom up, 3x plus 1 would be your factor. Or if you had a negative 2/5, we want to make sure the negative is applied to the top of the fraction. So we would read this as a 5x and a minus 2 as a factor. Or if you end up with something that divides, like we had over here, negative 4 divided by 2 was just negative 2. I like to keep the whole number as a fraction with a 1 under it. So technically 1x plus 4 would be the factor here. So if you just had a positive 4, it's just going to be an x plus 4 as your factor. Or again, if you want to look at that as a fraction, it's got a 1 in the denominator. Okay? So let's try this a couple more times. Or if you feel like you got it, or you have your own method, by all means, whatever works for you. Pause if you need to. Let's try this one if you're ready. So notice these all have something in common. They all have a 2x in common. I'm going to factor that out first. That's going to leave me 4x squared plus 5x plus 1. And so now this trinomial, I'm going to continue to factor. So inside the trinomial, the 4 times the 1 is what we're looking at now. I need factors of 4 that add to 5. Well, that's pretty easy. We used them. 4 times 1 got us the 4. 4 plus 1 gets us the 5 that's in the middle. So my factors are going to be 4 and 1. They're going to be divided by the first number. So divide by 4, divide by 4. 1/4 doesn't reduce, but 4/4 does. It's just 1, or 1 over 1. And now I can read these from the bottom up. 1x plus 1 would be one of my factors. And 4x plus 1 would be my other factor. And then just don't forget your 2x, your GCF, is also a factor. So your final factored answer has all 3 of these factors. Okay? Not bad, right? Pretty cool, if you ask me. Alright, let's try one more. So, again, I'm going to multiply first and last number. So 5 times 4 is going to be 20. Looking for factors of 20 that make 12. Like 10 times 2 is 20, 10 plus 2 is 12. Divide by my first number, which is 5. This is going to reduce to 2, or 2 over 1. So 1x plus 2 and 5x plus 2 would be my factors. Now there's just one small thing happening here, and I didn't really talk about it, but just assuming that you've seen this before. In these first 3 examples, we had what we call quadratic trinomials. If there's an x squared in the front here, then we have to have an x to the first here and an x to the first here, because that's going to get me the x squared, and then I have an x to the first here and an x to the first here to get my x to the first in the middle, and then of course my constant at the end gets me that product at the end. If instead of an x squared we have, let's say, an x to the 4th, then we have to accommodate that. So if there's 4 factors of x here, then 2 would have to go here, and 2 would have to go here, and this will all still work out. So again, this is going to multiply to get me 5x to the 4th. Then I have 2x squareds here, and 10x squareds here to get me 12x squareds in the middle, and then I still have my 4 at the end of this. So if your degree changes from a quadratic to something else, then you want to make sure to accommodate that in your binomials, right? So if you have a quadratic, if you have a square, then split the 2 up to 1 and 1. If you have a 4th degree, so you have a 4 here, split the 4 up to 2 and 2. And the only way this is going to work is if it's an even degree, or if this is half of this. So we have to have a quadratic-like expression there in order for us to factor the same way we factor the quadratics. Again, hopefully that's terminology that sounds familiar. Okay, so that's bottoms up. That's how I factor trinomials. Now, got 4 terms out of the way. Got 3 terms out of the way. If we have 2 terms and there isn't a GCF, or we're trying to continue to factor the 2 terms, we can only do it if they represent a difference of squares. That's probably one of the more commonly occurring ones. If you have something squared minus something squared, a difference of squares, then the difference of squares always factors into these, what we call conjugate binomials. That's where those binomials they match, right? They both start with A, they both end with B. The only difference is the sign in the middle. So these are conjugate binomials. That's, again, an important one. So if we know what we're squaring here and here, the bases of those squares are what's going to go into our conjugate binomials. So that's how I kind of work these problems. So for example here, x squared would be just like having an a squared here, but 16 doesn't really match b squared. So what I would do is rewrite this like 16, or the square root of 16 is 4. So this is really the same thing as x squared minus 4 squared. So instead of a and b, I have x and 4, which means here instead of a and b, I'm going to have x and 4. So once I know what I'm squaring to get each of these things, then that's what I put into my conjugate binomials. So my bases of my squares, my x and my 4, that's what I'm going to have in there. I'm going to have an x plus 4 and an x minus 4. And the order that you put those signs doesn't matter. So if you're more of a glass half empty person, you want to put the x minus 4 before the x plus 4, that's totally fine. Okay, so same thing here. To get a 9x squared, take the square root of 9x squared, you get 3x. So 3x squared here, and then if I took the square root of 4y squared, I would get 2y, so it's 2y being squared here. So this would be like my a and b. So instead of a plus b, a minus b, it's going to be 3x plus 2y and 3x minus 2y. Okay, so the bases of those squares go into my conjugate binomials. Again, 3x plus 2y and 3x minus 2y, or the reverse order, doesn't matter the order we multiply. Okay, skipping around, here's another. So if I took the square root of x to the 4th, I'd be looking at x squared, and if I took the square root of 81, I'd be looking at 9. So it's x squared and 9 as the bases of my squares. X squared is my a and 9 is my b. So instead of a plus b, a minus b, it's going to be x squared plus 9 and x squared minus 9. Now in this particular case, if you'll notice, the x squared minus 9 is still a difference of squares, so we can continue to factor. So this x squared minus, or plus, let me get rid of this. I can't do anything with the x squared plus 9. But the x squared minus 9, again, this is x squared technically and 3 squared, so I can continue. X squared plus 9 is going to stay, but this x squared minus 3 squared is like another a and b. So I can rewrite that x squared minus 9 as x plus 3 and x minus 3. Now you may be wondering to yourself or asking yourself why we can't do this. So let me just back up for a second here. You don't need to write this, but so you understand, okay? When I have these conjugate binomials, what happens when I multiply? Like an x plus 3 and an x minus 3. Well, obviously we're going to get back to the difference of squares, right? We got an x squared here, and I got a negative 9 at the end here. But in the middle, the negative 3x and positive 3x, they cancel. Those cancel because these terms are the same, but one has a plus and one has a minus. So the only way for this to factor into these is if I have, again, a positive and a negative, which means that last product has to be negative. So getting an x squared minus or plus 9 is not going to be possible. You can try to make these both positive, x plus 3, x plus 3. That's going to get you an x squared, and that's going to get you a plus 9, but you're also going to have 3x's here and 3x here, so you'd also have positive 6x's in the middle. And the same thing if you made them both negative, you would just get a negative 6x in the middle. The only way to get the middle terms to cancel and leave you with the two terms is if one's plus and one's minus, meaning that that product at the end has to be a negative. Okay, so hopefully that makes sense. Again, this is a review, so I know I'm going kind of fast, but this is all stuff that I'm hoping you've seen before. Alright, let's look at the next one here. So x is already written as a square. Here, if I took the square root of 100, I'm going to get 10, and the square root of y to the 4th would be y squared. So my a in this one would be x squared, and b would be 10y squared. So x squared plus 10y squared, and x squared minus 10y squared. Okay, now here, we're looking at cubes instead of squares, and hopefully you're recognizing that these are perfect cubes. Cubes are not as as friendly. I think the formula is a little bit more helpful when you're factoring the cubes, but just like with the squares, I have to know what I'm cubing. So like this is fine because it looks just like this, but 125 doesn't look like b cubed. So when I start this process, I want to start by making these cubes. So in the same way I would like square root the squares, let me cube root the cubes here. So x cubed, and then if I took the cube root of 125, I would get 5, so this is 5 cubed. So now I know what my a is and my b is, and then I can just kind of plug along with the formula. And the formulas are virtually the same. The only difference is, obviously, one's a sum, one's a difference. If I start with the sum, then my factoring will start with the sum, and then the next sign flips, and then the last one's always positive here. And notice that same trend here. If I start with a minus or difference, this starts with the difference, this flips to the opposite, and then this one's always positive. Everything else in the formula is the same. So a goes here, b goes here, a squared goes here, the product of a and b goes here, and b squared goes at the end. So let's try to factor, and in this one I'm focusing on my difference formula. So if I know what a and b are, okay, a and b, the bases of my sorry, I'm trying to clean this up. The bases of my cubes, again, my a and b, those are going to go into my binomial. So I know I'm going to start here with an x and a minus and a 5. And then my trinomial starts with an a squared. So in this case, a is x cubed. Or sorry, a is x. So it's going to be x squared. And then I have the opposite sign that I started with, so positive. And then I multiply a and b, so I'm multiplying x and 5, which would make 5x. And then I'm going to have a plus b squared. So b again being 5 means 5 squared is 25 at the end of this. So you're just applying a formula. It's really not that hard, and it's nothing I would make you memorize, although I have sort of the process memorized. So let me kind of talk you through how I use the formula without having to look at it. So I'm going to rewrite these as cubes. The cube root of 8x cubed would be 2x, so it's 2x cubed here. And the cube root of 27 would be 3, so it's 3 cubed here. So I know this is going to factor into a binomial and a trinomial. I know that basically what I have here is going to come into the binomials, the bases of my cubes and the same sign. So same sign here, this is going to be the opposite sign here, and we always end with the positive. So the bases of my cubes are going to be into my binomial. It's going to be a 2x here and a 3 here. And then to fill in my trinomial, it's just going to be squaring this, multiplying these two, and squaring this. Make that little smiley face there. So I'm going to square, multiply, square, and then I'm going to be good. So if I square this first term, 2x times 2x gets me a 4x squared. If I multiply my two terms, 2x times 3x gets me a 6x. And if I square this, the 3 times a 3 puts a 9 there, and I'm done. This would be all completely factored. Okay, and as always with factoring, you could multiply this out. It wouldn't be the most fun thing to do, multiplying a binomial times a trinomial. You'd have 6 times to apply the product rule. But if you were to multiply it out, combine like terms, you're going to end up with your 8x cubed plus 27. For myself, I probably wouldn't check everything, but I would at least check the first product, which should get me the first term, and the last product, which should get me the last term, and that definitely happens here. Everything else ends up canceling out if you manage the signs right and the formula right. Okay, so that's the gist of that. I don't know if we're going to see a ton of the cubes with our trig stuff, so if those ones you're a little shaky on, don't worry, but you definitely should be able to factor the trinomials, the differences of squares, and GCFs. Grouping, again, I don't know, but grouping is really just GCF, so hopefully you're comfortable with those. The last thing I want to mention is if none of this works, if no factoring is possible, then we call our polynomial a prime polynomial. I don't think we're going to see much of that with trig either, because we'll have to, if we can't factor, we would just be using another process. But important to mention in the context of reviewing factoring that if we can't factor, then what we're looking at is prime. So for instance, I have some prime examples. I know, terrible joke. This trinomial I could try. If I multiply 1 and 17, the only factors of 17 are 1 and 17 or negative 1 and negative 17, and neither of those is going to add up to 3. So I can tell that this isn't going to work. This is going to be prime. Okay. Again, a trinomial here. This one's a little tricky because it looks like it's going to work. So I get a 9 here, a positive 9. I could use 1 times 9 or negative 1 times negative 9, or 3 times 3 or negative 3 times negative 3. Those are the only combinations. Now, to get an 8, some of you might be thinking, oh, I'll use 9 and negative 1, but that won't get me a positive 9. So this one's kind of a trickier one. You're almost being set up there for failure, but none of the possibilities work. None of the combinations multiply to a positive 9 and a positive 8 when you add. And so again, this would be a prime polynomial. And then here, what I kind of showed you earlier. So a difference of squares we can factor into conjugate binomials. The sum of squares, not going to work. You can try to make this 4x plus 5 and 4x minus 5, but again, that's going to make a negative at the end. Or you can make them both positive, but that's going to get you 20 and 20, that's going to get you 40 x's in the middle. Or if you make them both negative, you're going to get negative 40 x's in the middle. There's no combination that's going to work. There's no way you can make that 16x squared and 25 positive without producing other terms in your expression. So this is, again, a sum of squares. A sum of squares is always squares, there we go, is always prime. Okay, so again, I know I went a little quick here, hopefully not too fast. Maybe you can slow me down in the video, I don't know. But this should all be review. You've all come out of college algebra, so this is definitely something that's hit hard there in previous courses. So hopefully the refresher was good. What we're going to do in the next one is apply all of these processes to our trig expressions, so hopefully you're solid. But as always, if you need any extra help, then reach out. Alright, till next time, take care.